Hi, my name is Michal Olejnik and I work as a rendering engineer at Infinity World Poland. I wanted to present to you work we did with Paweł Kozłowski from NVIDIA on Raytraced shadows in Call of Duty Modern Warfare. Here is our agenda for today. We will start by describing the motivation behind Raytracing and why we chose shadows. Next, we want to walk you through some problems we encountered during development. Some of those are specific to our title, but we mostly want to focus on general problems that most people will encounter when doing ray tracing, and give you solutions that worked for us and hopefully will work for you as well. Those topics include ray tracing in general from shader perspective, how to feed it with optimal data generated on the CPU, and how to denoise multiple lights per pixel at the same time. Note that any timings given during this presentation were collected on an NVIDIA RTX 2070 at 1440p rendering resolution. Let's begin with some background. For the start of our ray tracing R&D, we wanted to keep things simple. We felt that sticking to visibility-only algorithms will save us a lot of development time, since we don't have to care about shading, which left us with three main candidates: ambient occlusion, sun shadows, and local light shadows. And we chose local lights because we thought that using per-light acceleration structures will help us deliver better performance, both by keeping acceleration structure sizes small and by keeping any performance problem locals to those acceleration structures. As it later turned out, this was a good assumption that allowed us to achieve high ray tracing performance. But what are the benefits of ray traced lights? Well, unlike a hacky approximation provided by shadow maps, ray traced shadows are physically correct and give multiple immediately visible improvements. And we already had proper shading for area lights, analytical shading, so inconsistencies with shadow maps were even more obvious. Unfortunately, to keep things manageable, we had to operate under assumption that visibility and shading are separable, which isn't technically true. However, even so, ray traced shadows still provide vastly improved visuals. We started our work after most of the maps were done, so we had to make sure ray tracing will work without having to redo the lighting for those maps. That meant no specific ray tracing settings in editor. The only thing we had to work with were the physical light sizes already specified by the artists. We also had to make sure that we handle multiple lights. We have a hard limit of 256 lights per frame, and each pixel can have a different set of lights, either a different lights or lights in different order. So even if there are many lights per pixel overlapping, we had to make sure there is no flickering or sudden popping. We also had to care about predictability of the frame time. So we wanted to keep ray tracing execution time more or less constant, while allowing for picture quality to scale, depending on the load. We also wanted to evaluate quality improvements given by area shadows. Evaluating them at real time gives much higher frequency detail than what we can store in light maps due to storage concerns. For this purpose, we wanted to avoid aggressive spatial filters, because they usually need to have a big radius, which adds bias to the rendering equation, especially if we ray trace in lower than native resolution. So we aimed to rely mostly on temporal accumulation denoising whenever possible. So how do we go from hard shadow maps to soft ray trace area shadows without obliterating the performance? First, we have to build acceleration structures. There are two levels of acceleration structures in DirectX ray tracing API, and those are bottom and top level, so-called BLASes and TLASes. Ideally, we would build only one big acceleration structure for the whole scene. However, for real-time purposes, acceleration structure build times are non-negligible, which means we can't really afford to build everything from scratch every frame. So, we usually build individual surfaces of objects as separate BLASes and join them together in one big TLAS, or in our case in multiple TLASes. This way we have reasonable granularity. Individual BLAS build times and sizes are manageable, so they can be amortized between frames and then removed after source meshes are streamed out. However, too naive approach can have significant performance implications. During TLAS building, the TLAS does not have access to insides of BLAS, it just sees its top-level bounding box. This degree of separation is necessary. TLAS build times have to be kept on the low side, since they are rebuilt every frame. The problem materializes when multiple BLASes have overlapping bounding boxes. Regardless whether you need closest or any hit, what usually happens is that ray traversal has to test against multiple BLASes, so performance degrades extremely fast. Fortunately, DXR API allows for providing a list of multiple index and vertex buffers during build, so we can build multiple surfaces as one BLAS. This means you can provide it with a list of pointers to those vertex and index buffers. You don't have to reswizzle your vertex and index buffers to be in continuous memory range. Here is an example from our game, a worst case scenario. A light with not much geometry around. And here it is zoomed out. So how many objects could possibly fall into this light's influence radius? And here you can see the answer. Those are color-coded surfaces, and there is probably a lot more of them than you expected. What you actually see are geometry brushes that our level designer used for blocking out the map. Our map compiler aggressively merges those surfaces for more efficient work submission, which means that we usually have one draw call for all triangles with the same material, which is great for rasterizer, but is less than ideal for ray tracing, because now we have a lot of surfaces with overlapping bounding boxes. And here you can see the data on ray trace time depending on the BLAS merging granularity. As you can see, doing full BLAS merging improves ray trace times by about 6 times compared to doing no merging at all. The downside of BLAS merging is that you can't reuse geometries as instances. In other words, BLAS merging and instancing are two mutually exclusive features. For us, this wasn't a problem though. We have two main geometry types. One that you have already seen on the screenshots are brushes. Those are spatially huge, self-intersecting, they are relatively low polygon compared to the other type, and they have no LODs, so they are obvious candidates for being merged. On the other hand, we have models, which are used to fill in the detail in the scene. They are very small spatially, and they do not intersect very often. They are relatively high polygon and they use LODs, so to save memory, we can instance them. Of course, this means that we did not fully get rid of the overlap. In the case shown on the screenshots, we'll have one big brush BLAS covering almost entire map. So it will overlap with every model inside it, but for practical purposes, this is an acceptable performance trade-off. Note that this approach won't scale when doing whole scene TLAS. Fortunately, in our case, the solution will also be simple. Our streamer divides world into non-overlapping chunks, which we will be able to use for BLAS merging. So, for example, we can merge or brush surfaces for each chunk separately. It's important to note that BLAS building times scale badly for smaller poly count, so you need to provide the BLAS builder with enough work to make it worth the overhead of the build. Especially important is the CPU cost, so if you are doing your own ray tracing backend implementation, be sure to use DX12 multi-threaded command lists, otherwise it may become a bottleneck in your pipeline. Fortunately, this is something that keeps improving with newer drivers, so perhaps in the future it won't be a problem anymore. Here you have CPU and GPU timings for BLAS building on different character LODs. This is both before and after content optimizations. As you can see, the performance does not scale linearly with geometry complexity. After we are done with building our acceleration structures, we can finally ray trace against them. To achieve high ray tracing performance, we should avoid using expensive feature unless absolutely necessary, which is actually an area where visibility-only algorithms shine. For example, we do not need per-material shaders and we don't need recursion. We also do not need closest occluder, we just need to gain information whether there is any occluder at all on the way to the light. So in practice, our ray tracing shader setup is quite simple. We only have one ray generation shader and one miss shader to flip the visibility bit during raycast. We have a shared closest hit shader for all materials. And the only performance caveat is that we need any hit shaders. One for alpha testing, which is quite expensive as you will later learn, and one to add some ray bias for mismatched geometry. More on that also later. So, assuming we have acceleration structures built, raycast is very easy. We can use reconstructed workspace position from the depth buffer and cast a ray from this point towards the light by importing sampling a capsule shape. And we don't even really need to build a BLAS for the light shape to check for the hit. We can simply set the max trace distance to our important sampling point on the light. Then, if there is no hit along the way, a miss shader will be called and it will flip the visibility bit stored in the ray payload. In simplest case, we would only need one bit in the ray payload and a miss shader to determine the visibility, since DXR API allows us for not providing a closest hit shader at all. However, our denoiser uses shadowcaster velocity for tuning temporal convergence. So we want to return that in the payload. To avoid any extra memory fetches in the closest hit shader itself, we use the system semantic instance ID and the unused bits in it to encode a compressed velocity value. One should note that we use accept hit and end search flag, so we are not really querying for the closest hit. However, for practical purposes, we didn't notice any errors. This is probably because the dynamic shadow casters that actually use the instance ID bits are non-overlapping with other geometries, so they are usually tested correctly as the first one, so the correct velocity is returned. Unfortunately, we are unable to solve performance issues with alpha testing. And there is no easy solution here. Alpha testing requires dependent memory fetches, so first you have to fetch your triangle indices to construct the actual triangle. Then you have to fetch per vertex UVs, and only after that you can fetch the actual texture, so there is a lot of dependent additional work to be done. And this work cannot be moved outside of any hit shader to the ray generation shader, because it affects ray traversal. Alpha testing has been an object of extensive research for ray tracing, and one idea was to use high poly opaques instead of low poly objects and an alpha texture. But for practical purposes, to match the quality given by the alpha texture, those objects would have to have an extremely dense meshes, so it would probably not be faster at all while also taking additional storage. We had some ideas how to work around this problem, but those ideas never made it past the prototyping stage. One of them was to detect if given TLAS has any alpha tested geometry and lower the effective ray count accordingly. Other idea was to adjust ray count based on a previous frame ray generation execution time. Fortunately, since we shipped, some promising research on potential alpha testing hardware support has been published. As previously mentioned, we have cases where geometries in acceleration structures do not strictly match the geometries used with rasterizer. This concerns geometries generated using vertex and geometry shaders, but even after porting them to compute, it still would be not possible to build them because DXR API lacks API for indirect builds, so we would need to know index and vertex count on the CPU, which is not possible for GPU-driven data, unless we would do some kind of readback from the GPU to CPU, but this adds latency and its own set of problems. To work around this problem, we thought of biasing minimum trace distance to avoid self-occlusion artifacts. We needed to determine object type on per pixel basis, for example by using a stencil buffer. However, we did not have enough stencil bits left for our needs, so we came up with a different solution. By using a bias value in any heat shader, we can have different biases on even per object basis. We previously scrutinized performance of any heat shaders in relation to alpha testing. However, they are not that slow if you don't too much work in them. We use any heat shader to reject hits below certain threshold. There are a couple different hard-coded thresholds for different types of features, for example subdivision and tessellated terrain. And we encode index to those thresholds in unused bits of instance ID to avoid any extra memory indirections. So this works exactly the same as our velocity fetches. Of course, the two approaches described are a bit different because stencil biases per receiver and any heat shader biases on per caster basis. But since we wanted mostly to avoid self-occlusion artifacts, the any heat approach was preferable anyway. Here you can see a tessellated terrain with blank spots on it due to mismatched geometry. And here it is after applying the any heat fix. So how does ray tracing fit into our denoising pipeline? Call of Duty Modern Warfare uses forward plus shading, which means we have a lot of specialized material shader permutations. Shaders require recompiling after each driver or game update, so we didn't want to bloat game with even more permutations. We knew that any new code added to F+ shaders would be present everywhere, even if it was inactive, including our min-spec computers. So we had to make sure it won't add any extra overhead, most notably register pressure. Our end goal was to have a simple texture that can be point sampled by the F+ shaders, where each texel contains a floating point visibility values for multiple lights. Here you can see the high-level outline of our whole GPU side implementation. There are 4 main passes. First, we resolve the light indices from our light cooling system and do load or ray balancing. This information is fed into the Raytraced pass that we discussed before. After that comes temporal reprojection and accumulation pass. At the end, we do a spatial blur and do an integrated upsampler in the same pass. But before we go into details, let's take a look what it looks like in practice. Here you have a screenshot of our exponential shadow maps, a stochastic method for very soft shadow maps. However, it experiences light leaking and misses some details due to limitation of raster resolution. And here is a Raytraced point light. As you can see, the shadows are pixel perfect. However, in most cases we will want to use ray tracing for soft area shadows. So here is what a raw input looks like. This is a 4 rays per pixel in half resolution. As you can see, the result is very noisy. This is why we need a denoiser, because we can't really brute force the ray count too much not to lose performance. But before I show you the denoising process, let's see what our temporal anti-aliasing algorithm can do. As you can see, it's pretty good by itself. Not perfect, but it can be used as some emergency fallback, as I will show you later. And here is what the output of actual temporal denoiser pass looks like. Doing temporal denoising on separate visibility buffer containing only the spot shadow visibility information allows us to achieve much greater quality when compared to TAA algorithm that has to work on end color frame. Of course, we also have a spatial blur, but it doesn't really contribute that much when temporal denoiser had time to converge and the shadows are already soft. Note that all we do during the denoising process is done in half resolution on both axes, so we have 25% pixel count total. For each texel, we store 4 separate channels containing light visibility. That means we can denoise up to 4 lights per pixel, which is plenty, but there are cases when there can be more than 4 shadow lights per pixel. And we didn't want to force our lighting artist to redo lighting for those specific locations, so we added a fallback that stores not denoise visibility for extra free lights, so we can have up to 7 lights per pixel total, and the non-denoised visibility is stored with 1 bit precision. It is being carried over during the denoising process, though it is only touched by the final F+ shader. Thankfully, our temporal anti-aliasing, as I showed you before, is pretty good at denoising at itself, so those places are not too jarring. We wanted to keep all our data in the same UAV, because according to multiple benchmarks, having one texture fetch of 4 times wider texture is usually at least twice as fast than sampling those 4 textures separately. We also use variance-based filtering based on the ASVGF paper, which is famous for being implemented in Quake 2 RTX. 4 lights per pixel requires a lot of storage, so our UAVs are quite fat. Fortunately, we are able to avoid sampling all data at all times. For example, Spatial denoiser does not have to sample auxiliary RG32 texture when sampling its neighborhood for spatial blur. And to compute variance, we need to store both first and second visibility moments for each channel separately. So this means that we store the value of the signal of the visibility and also the square of the visibility. After the first pass, we also keep per pixel normals and depth in the same UAV. That way we can avoid extra memory fetches from separate textures. There is also some other data that is needed for various heuristics that determine temporal and spatial filter strengths. The first pass in our denoising process is the Indices resolve pass. We have a highly optimized light cooling scheme for F+. However, it does not check for spot shadow falloff during cooling itself to avoid fetching light descriptors. Falloff is only applied during F+ shaders, because this is faster overall for the rasterizer. But with DXR, we want to skip any unnecessary rays, so we want to apply falloff before a raycast. This is what Indices resolve pass does. It reads the light cooling bit mask, applies falloff, and writes to an intermediate RG32 UAV, which is later read by Raytraced pass and also the Upsampling pass. And because of the Outsampling pass, we output indices in full resolution, so we can upsample properly without artifacts. For example, this is the output of our tile cooling system. You can see a heat map of the number of lights on per tile basis. And here it is what happens after applying the spot shadow falloff. The effective light count is much smaller. Since we already have access to number of lights per pixel, we can trivially extend this pass to do load balancing. For each thread group in the original pass, we downsample the total light count, so that we have a total light count per tile. Then we add an extra downsampling chain until we reduce this value to only 1 pixel. This 1 pixel value contains a sum of total lights for entire screen. By using this value, we can make decision of how many rays per pixel we want to cast. So, for example, our target is to cast 4 rays per pixel on average, assuming half resolution. So, for example, if we have 1 full screen light, we naturally cast 4 rays per light for each pixel. On the other hand, when there is more lights, for example 4 lights, then we can only cast 1 ray per light per pixel. But this also goes the other way around. If lighting conditions are simple, for example there is only 1 light and it covers only half the screen, we can up the effective sample count to increase the quality while maintaining stable performance. The Raytraced pass uses computed indices to determine per light visibility. Then it passes this information to the temporal denoiser. The temporal denoiser itself is a pretty standard temporal accumulation scheme with a feedback loop. There are a couple caveats though. We want to apply a rejection per each bilinear sample. For example, we do not want to reject based on depth after bilinear filtering, so we want to implement bilinear filter ourselves instead of doing the hardware fetch. To avoid ghosting on moving shadows, as previously mentioned, we tune out temporal filtering when shadow caster velocity is non-zero. We also accumulate both first and second moments of the visibility, so that spatial denoiser can estimate variance over time using those moments. As an example, here is a heat map of temporal history length with character and camera in motion. Temporal history is stored on per pixel basis. So for example, any pixel that wasn't visible in previous frames and is visible in current frame will lack temporal history. This can happen for pixels that were previously occluded by, for example, a character model and were simply out of screen due to camera movement. Here's another heat map. We apply similar rejection scheme based on the shadow caster velocity or for moving objects themselves. One interesting issue we run into is that we can't make assumption about exact math done by hardware when picking samples for gather instruction, simply because we do not know the resolution of hardware interpolator. We can't query hardware for texels touched during gather with given UV value, simply because HLSL does not expose such function, so we have to do all the work ourselves. In our case, we have 2 UAVs with 6 channel total, so instead of doing 6 gather operations, we ended up doing 8 loads, which lowered performance a bit, but ensured no temporal accumulation errors occur when using odd resolutions. Another interesting performance caveat is how to match light indices between samples, and this is something that applies both to temporal and spatial passes. In our case, each pixel can have a different set of light affecting it, so even if 2 pixels share same lights, it's not guaranteed they will be in the same order. This isn't something that can be pre-computed. We have to loop over lights for both samples manually. So with naive implementation, we end up with dynamic register indexing, which is something that is not supported by DXC compiler and is not supported by actual hardware. What usually happens is that DXC either emits code that goes through memory or a lot of inefficient LU magic involving conditional masks and swaps. This is usually easily remedied by manually using LDS or group shared memory, but in this case we can do even better. Thankfully, our visibility for 4 lights is stored in one DWORD. In other words, we have 4 8-bit values packed together in one 32-bit value. And instead of unpacking it ahead of time, we can unpack it on demand. Unpacking 1 byte float from a DWORD involves a bit shift, so we can simply make the bit shift amount dependent on the matched light index. This avoids dynamic indexing and simultaneously reduces register pressure. In our case, it gives an improvement to the whole spatial denoiser of about 20 to 30%. After temporal denoising, we move on to spatial denoising, which is a simple, non-separable Poisson disk blur pass. We apply weighting heuristics that include depths, normals, and variance. Since we denoise multiple lights at the same time, we cannot use variance to scale the sampling radius, so instead we keep the radius fixed and we modify sample weights based on variance. Note that spatial filtering introduces bias to our shadows, so we want to keep its strength low if it is not needed. As temporal accumulation collects more frames, variance goes down, so we fade out the strength of the spatial denoiser. Outside of that, variance filtering allows us to avoid overblurring of context shadows or point light shadows. Here you can see a heat map of variance. Noisy because variance estimation is only doing over time during temporal pass. You can also see the heat map of variance weights during spatial filter. As you can see, using those weights will make sure that we don't overblur context shadows. Here you can see the whole denoising process. If temporal denoiser has time to converge, spatial blur and TAA will only add minor refinement because the shadows are already soft. So what happens in our cases when the temporal denoiser does not have time to converge? Our variance estimation is temporal only, so we are left without variance knowledge if disocclusion occurs. In such cases, we simply turn off variance filtering and apply a fixed filter. This results in very arbitrary filtering, so artifacts can be visible. Fortunately, our temporal anti-aliasing is very good at denoising, so we won't notice that in motion unless you encounter an extremely big light with dynamic occluders around. We did consider adding an extra spatial variance estimation pass, but to truly make it worth it the cost, we would need to ensure high quality without sacrificing performance. To amortize denoising cost, we do upsampling in the same pass as spatial denoiser. We use group shared memory to share visibility values between neighbors and do bilinear filtering for missing pixels. Full resolution indices from the first compute pass are used to avoid any artifacts. And the final texture is sampled by F+ shader, and it is in full resolution. It contains visibility for both denoised and non-denoised channels. The non-denoised channels are simply copied over at the end of spatial upsampling pass. But what about artifacts on compute group edges? Since we cannot access visibility from different compute groups, we have to guess values for border texels. We could make compute groups overlap by duplicating work of border threads, but in practice we found it to be an overkill. We already jittered in time which sample of 2x2 neighborhood we pick for our half-res textures, and with twice TAA jitter of projection matrix, we have 8 unique samples in 8 consecutive frames, which makes all errors imperceptible. Here is an example of what I'm talking about. Notice the doubled pixel or compute group edges before adding jitter. This can be a visibly distracting pattern, though only on flat surfaces spanning multiple tiles. After applying jitter, it is virtually imperceptible. Upsampling was the last part of our denoising process, so let's sum up what we learned. During the talk, we outlined a couple problems that we still need to solve. Alpha testing will most likely have to be replaced with high-poly opaque BLASs. But actual performance mesh complexity balance is yet to be measured. Mismatched geometry is the biggest concern, since modern vertex shading pipeline seems to evolve in completely orthogonal way to ray tracing with advent of mesh shaders. And finally, we need to improve our spatial denoising scheme. NVIDIA Raytracing GameWorks provides a good spatial denoiser, but it's not suited to denoising multiple lights. It's worth investigating how it could be integrated with our framework in performant way. However, many things went well for us. Barring alpha testing, our ray tracing is very performant and it scales well with content. The execution cost is more or less constant, regardless of light count. Most importantly, it works well for all lights. Our artists did not have to redo lighting or turn off ray tracing for individual lights. When ray tracing is on, all lights are ray traced. Here you can see the average ray tracing performance. Our load balancer maintains constant cost of the ray tracing pass, which is usually about 1.5 milliseconds and rarely goes above 2 milliseconds, unless the location has a lot of alpha tested objects. The total cost of the whole denoising and ray tracing passes is less than 3 milliseconds. Here are some in-game examples of our denoiser in action. Proper area light shadows give desired soft look. They also help to ground objects in their surroundings. They do not experience leaking and ensure penumbra widening with distance from the shadow caster. We wanted to thank Oleg and team from NVIDIA for their help with our work. And if you have any questions, feel free to contact us by email. Thank you for your time.